Hello everyone. In this video I'd just like to talk you through a physics principle known as Hooke's law, and we'll reference what the elastic limit is. Now Hooke's law is a topic usually taught in the context of energy and energy transfer, usually in Key Stage 3 and 4, but I'm aiming this video primarily to Key Stage 4 students. Let's think about what Hooke first of all discovered. And he said that the more force you put on a material, and we're going to talk about a spring as an example, the more that material stretches. So fundamentally, he said the greater the force that you apply, the greater the stretch observed. That's key things. So the greater the force, the greater the stretch. And this is true, this applies, provided what's known as the elastic limit of the material is not exceeded. Now, when you stretch a material, it gains elastic or stretch energy. And every material has a particular elastic limit where it will extend in a uniform manner, but beyond that particular point it won't. And this is what Hooke discovered, that the more you force you apply, the greater the stretch, provided you don't go beyond this elastic limit. So if we were to draw a very quick sketch on a graph how this would look, if we had, let's just put force at the top, represent that with F, and let's say we're measuring extension on the bottom, and that would be, let's call it E, you get a very characteristic graph. It looks a little bit like this. So we get this uniform or proportional rise, and then what appears to be a dip. And at this point here, if we just call that point P, that is the point where it stops obeying Hooke's law. So we'll just write that down there for reference. So that point P is where we stop obeying Hooke's law, because we're going beyond the elastic limit. And in that case, the material won't return to its original size when the stretching force applied is too great. Now, since force is proportional to extension, you can actually express Hooke's law as this. F is proportional to, and often we see extension written as an X. So F is the force applied, and extension of the material given by the X here. And if we're thinking of units, force would be in newtons, and typically extension in meters. So they would be the units that we're going to use. Now, because it's proportional to extension, we can actually develop that further and put in a constant. So we can actually say that the force is equal to, and we use this value K, Kx. Now K is referred to as the spring constant. And this can vary from material to material. So we've said the force is proportional to the extension. So we link those two together by having this spring constant. And clearly the spring constant would have units of newtons per meter. If we rearrange the equation and send x onto the other side, it becomes a dividing factor. So it would be F divided by x, so newtons divided by meters, newtons per meter. So K is called the spring constant, and it sort of measures the stretchiness of the material, if you like. So let's just draw, again, 3 very quick sketches to represent 3 different types of spring that you can see. So on each sketch, if I just draw these very quickly on to scale, and each y-axis rather, is force, and if we said extension, this time we use the actual symbol x, is on the x-axis, you get something that looks a bit like this. For a stiff spring, you'd see a proportional rise like this. So for a given force, it would take a little while to be able to extend that very easily. For a softer spring, you'll notice that the gradient decreases, it's a bit of a shallower rise. And for an even softer spring, you'll get something that looks like this. So for a very small force, you get a very large extension. So if we were to draw an arrow here, we can see we're sort of midway on the x-axis. If we stick at the same point here, you can see we're a bit further along. At the same point here, you can see we're much further along on that x-axis. So we've got a stiff spring, a softer spring, and we'll put a very soft spring. You get three distinctive looking graphs there. So let's think about an example question you might get. So in a particular physics paper, you might get a question that looks a bit like this. In fact, we'll shrink the screen a little just to make a bit more room, move things up a bit. And here could be one example question. So we'll just work this one through. So here's the question. A spring is 0.38 meters long. So it tells you that the total length of the spring is 0.38 meters long. When it's pulled by a force of 2 newtons, so we're told F is 2 newtons, it stretches to 0.42 meters. So it's been stretched to 0.42 meters. And they might ask you, what is the spring constant? So, in this case, we know that F is equal to Kx. If we rearrange that to get K, what you end up with is F divided by X, the force divided by the extension. And you'll notice, if the original length is 0.38, and if we've stretched it to 0.42, we've essentially extended our spring by 0.04 meters. So if we finish this equation, 2 divided by 0.04, and if we work that out on a calculator, what you'd end up with is a value for the spring constant K. So 2 divided by 0.04 is equal to 50. So we'll just shrink the screen just that little bit more. In fact, we'll move this up here just so we can write that clearly in. So in this case, what we've got is a spring constant of 50. But remember, we need units, newtons per meter. So you might get given a very, very simple question like that and just be asked to work out what the extension could be, what the force could be, or most commonly what the spring constant is. And that's what we've had to work out in this example question. If we look at the graph, just going back to these particular graphs we've got here, we can see that for a stiff spring, a force produces a small extension compared to a soft spring. And you might be asked, the reason I'm going back is because you might be asked to actually analyse these. So I just want to reiterate that point. And for a soft spring, even a very small force will produce a big extension. So you might be asked numerically to work out a spring constant or comment on something like that based on a particular graph. Okay, so that's just a little bit about Hooke's law and the elastic limit. More often than not, when it's done in lesson, it's done with a practical way. You sort of have a table and a clamp, and you attach to a clamp a spring, and you put a known mass on top of the spring, and with a meter ruler you can measure that extension. And usually you can get a graph of force against extension for that. And you should see this at the top here, this kind of characteristic graph. And if you keep adding masses, you'll notice that eventually it will stop obeying Hooke's law. The graph will start to plateau and then take a dip. So that's a little bit about Hooke's law, the principle behind it, and how to work out the spring constant. Okay, hope all that helps.